Hello, my name is Berman and I just graduated my master's degree at the Technion Israel. Today I want to present you joint work with my supervisor, Professor Roth. This work deals with two enumeration problems which are motivated by coding applications. We'll start with the introduction, introduce them, and proceed with lower and upper bounds, characterization of the combinatorial objects. We'll deal with them today, and finally a studying of the average case. I now introduce some notation. F is a finite field. Mn is the set of monic polynomials of degree exactly n over f, and Pn is the set of monic polynomials of degree at most n over f. The first combinatorial object is a maximal polynomial. Given a positive integer m and a polynomial S6 of degree at most m, we define phi of s to be the number of distinct factorizations of S6 over f. And epsilon m is defined to be the largest number of factorizations that can be realized by a polynomial of degree at most m. And we call a polynomial of degree at most m that realizes this maximum a maximal polynomial. It is easy to see that the maximum is attained only when the degree is exactly m. In 1984, Pire showed an upper bound for epsilon m over GF2, this upper bound, and his motivation was to show that most binary shortened cyclic codes approach the Gilbert-Vershamov bound. We improve the bounds for any q, and we show that epsilon mq equals 2 to the m divided by log qm. We are now define a restricted problem. The idea is similar to what we have already described, except that now, instead of enumerating all factorizations of a polynomial, we enumerate factorizations that satisfy a certain property. And this property is as follows. Given a positive integer n and a polynomial S6 of degree at most 2n, we say that the factorization of S is an n factorization if both of the factors ux and bx have degree at most n. And in a similar way, we define phi n of s to be the number of distinct n factorizations of S6, and epsilon nn is defined to be the largest number of n factorizations that can be realized by a polynomial of degree at most 2n. We say that a polynomial S6 of degree at most 2n is n maximal if it realizes this maximum. The motivation for studying this combinatorial object is list decoding of arithmetic codes. In recent years, there has been a growing interest in arithmetic codes, and in particular in their list decoding performance. Some 30 years ago, Roth present a construction of arithmetic codes. He called it diagonally interpolated codes. And in 2017, he he showed a list decoder for these codes. And where the array size is n plus 1 times n plus 1, and the minimum rack distance equals 2, and the list decoding radius 1, he showed that epsilon nn is in fact the largest list size for this code and this list decoder. He also showed that over large fields, the list size is exponential, 4 to the n, but there was no analysis for this problem over small fields. So in this work, we show that over small fields, the list size is sub-exponential, and moreover, the average list size is linear and the variance is polynomial. So this is the motivation. And now to state the related combinatorial problems. The first one with ordinary factorizations, given a positive integer m, compute epsilon m and characterize the maximal polynomials in mm. And the second one, given a positive integer n, compute epsilon nn and characterize the n maximal polynomials in p to n. We start with the lower and upper bounds on epsilon n and epsilon nn. So it is easy to see that for all polynomial Sx of degree at most 2n, since in phi and S we enumerate only the n factorizations and not all of the factorizations, we have this inequality, and thus upsilon nn is smaller than upsilon 2n. Therefore, it is sufficient to prove upper bound on upsilon m and a lower bound on upsilon nn in order to get lower and upper bounds for both expressions, for both values. So we showed that the log of upsilon m is smaller than m divided by log qm, and similar expression for lower bound for upsilon nn, and conclude that upsilon m equals 2 to the m divided by log qm, and a similar expression for upsilon nn. So it is sub-exponential over small fields. At first, in order to get these bounds, we investigated the structure of the maximal polynomials and of n-maximal polynomials. Although we didn't use the full characterization to prove these bounds, we found it very interesting from a purely mathematical point of view, and I want now to present you the characterization. So first we need to introduce some notation. We take the monic irreducible polynomials over f, and we fix an order, an increasing order according to their degrees. For example, for GF2, we can fix this order, and we define di to be the degree of pix. Now, given a polynomial Sx, we factorize it into a product of irreducible polynomials, factors. Ri is the multiplicity of the factor pix, and we set the histogram of Sx to be the vector of the multiplicities. Of course, there is a one-to-one correspondence between histograms and polynomials over f. We define rho of S to be the maximal multiplicity of any linear factor of S. Here, just for example, take this polynomial already factorized into reducible factors, and this is its histogram, and we demonstrate it in this graph, where we attach for each degree, here di, the degrees of irreducible factors, we attach for each degree a color. We can see that rho S is equals 3 here. So I wrote a program that calculates maximal polynomials, histograms for maximal polynomials, and here for in this example, we can see that there is a specific structure of maximal polynomial. We can see that the histogram has no gaps here. There are no zeros coordinates. It is monotonically decreasing. It decreases rapidly. There is a long tail of ones. And we proved all these properties. In order to prove them, we used an explicit formula for the number of factorizations of a polynomial S. It is very easy to see that we have this formula. It is also easy to see from this that the degree of a maximal polynomial must be m. And the first structural properties is that the histogram is monotonically decreasing. In particular, it is all positive. In all our results, we use a general proof method. We assume that a polynomial S of degree at most m does not satisfy the property to be proved, and we construct from S a polynomial S tilde, for which S tilde has more factorizations than S, and conclude that S cannot be maximal. We proceed to this proposition, which relates the degree di to the multiplicity Ri of an irreducible factor of a maximal polynomial. The meaning of this proposition is that for any irreducible factor of a maximal polynomial, its multiplicity Ri is inversely proportional to its degree di with factor rho. And this explains why the histogram decreases rapidly. But the multiplicity Ri is not completely determined. Here we determine the maximal degree of any irreducible factor, dt. We showed that it is log qm, roughly. And we gave an estimation of rho. Recall that rho is the maximal multiplicity of any linear factor of S. We show that rho equals log qm divided by ln 2 plus minus a small error. We can see how this properties, how the histogram demonstrates these properties. But we can see that although the property we show, the multiplicities are not completely determined according to the properties we showed, here at the numerical results, we can see that the tail of the histogram is completely very clear what it is. It is just a long tail of ones, for example. So we also proved this theorem, which improved the characterization for large DIs, degrees. And again, this theorem gives a relation between the degree DI and the multiplicity RI. But we can see that for large degrees DI, it is actually completely determined the multiplicity. For example, if we substitute Ri equals 2 in the theorem, we get that Ri is larger than 1 only when Di divided by log Qm is smaller than 0.585. And if we recall that dt is log Qm, we conclude that for given Q and M goes to infinity, almost all of the multiplicities in the histogram are 1. And in fact, all but a vanishing fraction of the multiplicities are 1. Now we proceed to the characterization of n maximal polynomials. A reminder, we say that the factorization of a polynomial of degree at most 2n is called nn factorization if both of the factors ux and vx have degree at most n. And polynomial Sx is n maximal if it has a maximum number of nn factorizations. Introduce quickly some notation. We defined R0 to be 2n minus the degree of S, and D0 to be 1. And then we extend the histogram of S to be the concatenation of R0 with the histogram of S, and rho n to be the maximum between R0 and rho S. So here, just to demonstrate what is R0, here this polynomial for n equals 7, this polynomial has degree 11, and thus R0 equals 3. And we get that the rho n is 3. This is the extended histogram. And what we show that actually the same structural properties as for maximal polynomials holds here for n maximal polynomials, where we replace the degree of the polynomial to be 2n, we take the extended histogram rho ns, and we allow the index to be 0. And there is a huge difference here. In the ordinary factorizations case, we have an explicit formula for the number of factorizations of polynomial, but here we don't have explicit formula for nn factorizations, for the number of nn factorizations. And this is this makes the proofs much more intricate. It was more complicated. So here is, for example, the histogram for 90 maximal polynomial. We can see the same structure, but here we have this coordinate for R0. And this means that R0 equals log Qn. We have log Qn, and thus the degree of n maximal polynomial is smaller than 2n. It is 2n minus log Qn. And this is in contrast to the maximal case, to the ordinary factorization case, where we saw that given m, any maximal polynomial's degree exactly m. We can see here that actually, in order to have more flexibility to build the NN factorizations, we have less large degree factors, and in compared to the maximal polynomial. Now to the average case. For both the problems, we have different probability models due to the coding applications. Here, given a positive integer m, we set the sample space to be the polynomials of degree exactly m with uniform distribution, and we define a random variable phi m as follows: to attach for each s the number of its factorizations. We prove that the expectation is linear and the variance is polynomial. We have like m cubed. And therefore, from the well-known Markov and Chebyshev inequalities, we obtain this inequality and conclude that the probability of phi m being superlinear in m tends to 0 as m goes to infinity. By a different approach, using the Chernoff bound, we prove this proposition. And one can conclude from this that the median of phi m is sublinear in m. And now to the average case of NN factorizations. Here, due to the coding application of least decoding of rank metric codes, we set the sample space to be Pn times a product of Pn with itself with a uniform distribution. Recall Pn is the polynomials of degree at most n. And we define a random variable phi nn as follows: it attach for each pair uv the number of NN factorizations of the product uv. Here again, we show that the expectation is linear and the variance is a polynomial. It is behaves like n to the 4. And we conclude that the probability of phi nn being superlinear in n tends to 0 as n goes to infinity. That's it. Thank you very much for attending this talk, and I hope that all of us will have good health, and bye-bye. Thanks.